All right, good morning, everyone. I want to start off by, we're going to finish up our notes and then we'll do the worksheet from yesterday. The worksheet that was assigned for yesterday, which is related rates quiz reviews. We're not going to have a quiz, but I mean, it's going to be a test, but we're just doing it for review for now. But I do want to go over, this is the draft for the calendar for next week. I still have to confirm with Mr. Jones, but this is what I'm looking at. So we'll do, mainly today, we're just going to practice the problems that we've done already, just to kind of get more familiarity, get more comfortable with those types of problems. And then we only have one more type of problem to go over, and that's a shadow problem. That's also a similar triangle, but it's easier than the cone problem. So we'll do a little bit, we'll talk about L'Hopital's rule, which is kind of involves limits. It's kind of like a standalone, and we're just going to kind of stick it in with related rates. It's a simple concept there. So after we go through this, we'll be able to start reviewing for our, because we've covered everything that we need to cover, and then we'll start reviewing. And then Tuesday, we'll have the full period to review as well. And I'll go through exactly the type of problem that you're going to see.
Good morning. It's time for
Wednesday, asynchronous day, but I will have a morning session, 8:30 to 9:30. I'll create another test review. We'll go over that. I'll record it. So if you guys can't make it, you can always watch it later. And then Thursday, we'll have the related rates test. Morning review, 7:15. This will be recorded as well. And yeah, just over related rates, 2.6. And then may have L'Hopital's rule as well. But you'll know exactly what to expect on the test. Friday, we'll start our next unit, which is 3.1. Monday, Tuesday, we have no school. And then Wednesday is our first day of full face-to-face. And then I'm still trying to figure out the schedule for the week after next. So I'll let you guys know. But once this is finalized, I'll put this up on my website under calendar, so you guys can see if there's any changes. I'll let you know. Okay, any questions next week? Okay. I think we finished this problem, right? We finished the cone problem, but let me, I do want to recap and see if you guys have any questions after the recap. And after that, we will slide up. We'll do the Pythagorean theorem problem. That's similar, but then there's also some distinct differences with the latter problem. And then we'll go to the review sheet where we'll look at these problems that we've done already and just review these scenarios. So let me talk through this problem again. With cone problem, we start off with a diagram, label our parts. We know that we're starting with a volume equation for a cone. The difficulty of jumping to the derivative is having to go through product rule, and then after product rule, having too many variables and not enough information. So that was going to be the challenge of this type of a problem where we just don't have enough information after the derivative. So what we need to do is we want to find a way to merge those two variables together, to merge that radius and the height together. But before we can merge them together, we have to know what that relationship is, right? So I can replace one in terms of the other. So we go to our diagram where we can draw a triangle within a triangle, and we have one triangle that represents the dimension of the water that's inside the tank, and also the dimensions of the tank. But we do know that the water level, the radius and height are not going to stay the same, right? Water is being poured in. So as water is being poured in, you can imagine the amount of water is going to increase inside the tank. The height is going to be increasing. The radius is going to be changing. So we leave these as variables. Okay? We create our proportion. Small radius is to the big radius as the small height is to the big height. Cross multiply, we get 12r equals 5h. But still, even at this point, we don't know what to get our equation in terms of, right? We want everything in terms of r, or do we want everything in terms of h? So we have to look at the problem some more and see what other information is provided. We have dv dt. We're looking for dh dt. So this is really the hint. This is the big hint here. Okay. Whatever you're looking for is the variable that you want to use, or that you want to get to this dh dt. So because we're looking for dh dt, we want our volume equation as h. And the reason why we want h is because if we have our equation in terms of h, dh dt will just naturally show up when we find the derivative. Okay. Now, if you get everything in terms of r, there's still a way, it just takes a little bit longer. Okay, it's not as efficient to get to our final answer. I mean, you can solve for r if you want, get to dr dt, and then there's a conversion from dr dt to dh dt, but the fastest way is looking to use the variable that's related to what you're trying to find. We talked about how this 8, we got to be careful with this 8 because this is the water level at just a moment in time, right? Any moment before this is going to be different. Any moment after this is going to be different. So if we stick this 8 in too soon, we're changing the problem. We're saying that water level is pouring in, but that height is going to stay the same throughout the entire problem, and we know that's not the case. So we want to make sure we ignore that 8, and we want to hold on to that variable until after the derivative is found. And then once that is found, then we can plug in and we can find the answer for this moment in time. So dh dt indicates we're trying to get our equation in terms of h. So we create our proportion here. We solve for r because r is the variable that we want to remove. So we remove r, get in terms of h. And here, technically, we're ready for the derivative, but let's keep going, right? I mean, if we can avoid messy derivative rules, let's try to avoid it. So you could go through product, and chain, but why not just continue cleaning up so that you have a nice and easy power rule to use? So we expand, combine the coefficients, push the variables together, and now this is an easy power rule problem to do, right? This looks messy, but that's just a number that's going to hang out in front. H cubed becomes 3h squared. Both the v and h will produce their own d over dt. And once we have this, now we're ready to start putting information in. 8 goes in for h, 10 goes in for dv dt. We go through a series of combining values together. Leave pi out of your calculator. Okay, don't put pi in the calculator because we want to hold on to pi in our final answer. We want to leave our answer as exact as possible. And something else to be careful about is careful with the placement of that pi. If the pi ends up being in the denominator, we can't just move it to the top. You got to keep it in the denominator, okay? Pi in the numerator is different than pi in the denominator. You're changing the value if you move that pi between top and bottom.
How did pi get from the numerator to the denominator?
Oh, you mean from here to here?
Yes.
Okay, so I want to solve for dh dt, so I need to divide by a fraction, right? So dividing by a fraction is the same thing as multiplying by the reciprocal. So I'm multiplying both sides by 432 over 4,800 pi.
Okay, thank you.
When I do that, I'm able to see that pi ends up in the denominator, and that cleans up to be 9 over 10 pi.
Okay.
Good. Any other questions? We're going to revisit this type of problem in a second, or after we get through this example 4. But I want to know, it may take some time for us to get comfortable with all the steps. But what I'm more concerned about is if some step doesn't make sense, I want you to let me know so that I can help move you towards being comfortable with this type of problem. Okay, you guys good? All right, let's go to let's slide up to number 4, and this is a Pythagorean theorem problem. A squared plus b squared equals c squared, but let's work through this scenario here. All right, so number 4 here. We have Joe standing 6 miles east of Mo. So we have Joe initially standing 6 miles. Okay. Joe is walking north at 3 miles per hour. And Mo is walking south at 1 mile per hour. So we're having a bird's eye view of this problem here. But if you look, this doesn't quite fit into a nice triangle. So let's make some adjustment, right? Why don't we let Joe absorb the distance traveled here? Hold on, let me read the problem here. It says, Joe walks north 3 miles per hour. Mo walks south 1 mile per hour. What is the rate of the distance between them changing after 2 hours? So this doesn't quite fit into a right triangle or into one right triangle. So let's think about the merging of these two rates, right? After 1 hour, what is that distance between them?
4 miles.
4 miles, right? So what if we just let Joe absorb the rate that is changing between them? And let's just let Joe move at 4 miles per hour. And that way we can force our problem into something that's easier to work with. So let's have Joe move at 4 miles per hour. And now we still have the same relationship in terms of their vertical movement, but now we have an easier diagram to work with. Okay, so now I can create that relationship. And there's my Pythagorean theorem starting point. So just like the latter problem, we're going to find the derivative. So let's go down each term here. Okay, so what's x squared's derivative?
2x.
Mm-hmm. But we also need to include what?
dx dt.
Yeah, dx dt, right? Every variable is going to have its own time component. Okay. Same, we repeat for every variable, right? Y squared is 2y. Six variables, so let's look at what we can gather. Okay, let's go back to our problem here. Joe is standing 6 miles east of Mo. Where can we put that 6? That's x, right? Okay, that's that horizontal distance there. Joe walks north 3 miles per hour. Mo walks 1 mile per hour. So we combine those rates, right? So I put that here for Joe. Or we can put that 4 mile per hour. Okay, so y related.
Oh, would be dy.
Yeah, there's a time component. Yeah, I put 4 miles per hour here, but I refer to it. It's not really y value. But yeah, there's time component, so we need to put that here. Is it a positive 4 or a negative 4? Because why? What's happening to y?
It's getting bigger.
Okay, good. Yeah. The way we drew our triangle, this height is increasing, so we want that to be a positive 4. Okay. All right, any questions so far? Are we good? Okay. Let's look at what we're trying to find here. At what rate is the distance between them changing? Okay, what variable is that talking about?
Z.
Okay,
dz dt.
and it's a rate, so it's dz dt, yeah. So that's the unknown. All right, we're not ready to plug in, right? We have all these missing pieces here still. So here is going to be something that will help us out. We're looking at a specific scenario 2 hours into the problem. So maybe we can figure out what y is. So what is this distance? Okay, why do you say 8?
It's
4 miles an hour at 2 hours is 8 miles.
Good. So he starts off here, right? Well, for this problem, we're making Joe take in the speed of Mo walking. So after 1 hour, he's going to be 4 miles north of where he started. After another hour, he's going to be another 4 miles. So that's going to, so at this moment in time, he's going to be 8 miles north of where he started. Yeah, so we have to do a little bit more calculation than the previous problem, right? All right, any questions here? So this helps us out, right? How can we find z now? Yeah, Pythagorean theorem. A squared plus b squared equals c squared. Yeah, this is going to be a variation of the 3, 4, 5 triangle. So 3, 4, 5, 6, 8, 10. But if you're unsure, you can always plug in and find that z value. Confirm. All right, almost there, right? We need to find one more. We need to find 5 out of the 6 before we can find that 6th one. Okay, dx dt.
It's 0 because it's not changing.
Right, that horizontal distance is not changing, right? Joe is walking north, Mo is not moving. So you can imagine this x is not changing at all. That horizontal distance is still going to remain 6. So make sure we don't put 6 here, right? It's 6 at the beginning, it's 6 at the end. There's no change, so 0. So I want to point this out because not every problem is going to have a constant. And if there's a constant, it's not always going to be in the same place as the previous problem, right? For the latter problem, it was the hypotenuse. For this problem, it's the dx dt. We're going to see some problems on Monday where none of them are constants, so they're all changing. So it really just depends on the problem. So we want to kind of visualize the problem in motion, picture what's changing, and then let that guide your next step. So there's not going to be a formula for every problem is not going to be the same in terms of the rates. It just depends on what's changing and what's not. All right, any questions? Because we're now ready to plug in. Okay. So all these variables gets put into our derivative equation, and then we should be able to solve for dz dt now. Okay, this goes away nicely to 0. Okay, what's our unit of measure here?
Miles an hour.
Miles per hour. Does it make sense that we're getting a positive number, positive rate?
Yes,
Yeah.
because it's
Yeah, Z is growing, right? Joe is walking away further and further, so that distance is going to keep growing. So positive answer makes sense. All right, any questions here? Okay, let's go to the review. So this is under Thursday's link here. So very similar scenario from what we just did with example 5. So let's see if we can set it up. There's some things that are a little different, which we're going to get to, but your setup should feel pretty identical to begin with. Okay. All right, so look at example 5 and see how much of it you can carry over. And as you guys try to set this up, I will work alongside you guys. Okay, proportions here. Okay, pretty much identical, right? Same dimensions, same equation, same proportions. All right, let's read the problem. Let's read the rest of the problem here. Water is flowing out of the tank at a rate of 12 cubic feet per minute. So we need to read this description and see what variable that's talking about. What do you guys think? Okay, dV dt, good. Cubic feet, you know this is a three-dimensional unit, that must be volume. But it can't be just volume because there's time involved, so it's going to be dV over dt. And is it just going to be 12, or is there an adjustment we have to make? Yeah, water's flowing out, right? Water's flowing out. We know the amount of water in the tank is going to be decreasing, so we want our rate to be negative. Flowing out. Good. Any questions? Okay, let's look at what we're trying to find. Find the rate at which the water level is dropping. So what variable is that? dH dt, good. When the radius is 4 feet, so this is something different. Right. Our previous problem, we were given h, but now we're given radius of the water level, so maybe these are related, but we have something that looks a little bit different, right? But we want to kind of zero in on what we're looking for, right? Because we want this to guide our decision about our volume equation. So because we're looking for dH dt, what will be the most efficient way to get to dH dt? What do we want our volume equation to look like on the right side? In terms of what?
H.
Yeah. H will just naturally produce dH dt for us. If we do R, it'll produce dR dt, which we can still get a dH dt, but it's just it's an additional step. So this dH dt is going to help guide our next step. We want our volume formula as H. So that's going to help decide or help our next step, right? We want to replace R. We want R to disappear. We want the right side to be just showing H so that we can get that dH dt to naturally show up for us. So I'm going to solve for R. R equals 5H over 12. So pretty much the same thing that we saw in the example previously, right? We're just going to pretty much going to get down to the same volume equation as before. But we can practice our steps, right? Okay, we keep working, right? No derivative yet, right? We want to find the derivative when everything is nice and clean and no messy product chain rule here, if we can avoid it. Okay, so this is the place that we want to be before we find the derivative, because if you look, this is a very nice and clean power rule. I mean, this fraction looks messy, but it's just a number, right? So the derivative should just be with the v and the h cubed, and the coefficient just hangs out, right? Just hangs out in front. Okay, so we find dv dt. Coefficient stays. H cubed becomes 3h squared, but we also need dh dt, right? So technically I can start plugging in, but I'm going to do a little bit more cleanup there. I'm going to push that, put the 25 and the 3 together. Oh, this should be cubed. Oh, sorry, squared. Okay, good so far. So if we try to plug in, right, the negative 12 fits in nicely for dv dt. We want to solve for dh dt, so it's good that the dh dt showed up. But there's something that we don't quite have. We don't have h. But maybe there's something related that we can use. We don't have the height of the water level, but we do have the radius of the water level. Is there some way that we can maybe connect and find a way to connect between these two variables or these two values? How can this 4
The
help?
ratio?
Yeah, we have the ratio, right? So, yeah, so any of these we can use to help us get to, right? If I have height of the water level, I can find the radius. If I have the radius, I can find the height, right? We have that connection.
So the H for R12 over 5.
I'm just going to plug into this and then solve. But yeah, you're doing your way works perfectly. So we got to do a little bit more work, but we were able to get there, right? We weren't given directly what we need, but we have tools to help us get to where we want to go. Now we're ready to put that 48 over 5 in for the h. Okay, so we have everything we need now. Okay, dv dt. Okay, these are large numbers, a little messy, but we have our calculator, so just take it a piece at a time and work your way down. Again, hang on to pi. Don't put pi in the calculator, otherwise you're going to lose that exact value. $75 times 48 squared, 432 times 5 squared. Okay, so it's a messy fraction, but it actually cleans up nicely. Okay, so we're almost there, right? Divide both sides by 16 pi. Notice, though, where the location of the pi is, right? It's in the denominator, so it needs to stay there. We can't just move it up. Okay, what's our unit of measure?
Centimeters a minute.
Yeah, you have the right idea. I think for this problem it's feet per minute. Okay. Okay, good. Does the
Yeah, I just remember
sign?
the last problem.
Oh, I see. That's fine. What do you? Does the negative make sense for our problem?
Wait, would it be cubic feet per minute?
Okay. Yeah. Why would it not be cubic feet per minute?
2D.
Yeah. Cubic feet is going to be volume, right?
Okay.
So height, radius, length, it's all one-dimensional. So feet.
Okay.
Yeah. So the only time you're going to see something different with your length, your top is going to be area. Area is going to be square feet. Volume is going to be cubic feet. But everything else is just going to be one-dimensional. Okay. All right, good. Does the negative make sense for our problem? Negative rate for the height?
Yes.
Okay. The water is flowing out, so everything is dropping, right? Radius is decreasing, height is decreasing, so this negative is consistent with what we know to be true about this problem, right? Okay. All right. Very similar setup, but I want us to get comfortable with this process, right? Being able to substitute, decide which variable to use, clean up, hold off on using R or H until the derivative shows up, and then being able to be careful with your cleanup step, making sure you hold on to pi if it's in the denominator, to keep it in the denominator, to be able to identify the correct units of measure. Okay. All right, any questions for number one? Okay, look at number two. Virtually identical problem, but what's the difference?
We're finding the radius.
Okay, so what variable are we looking for?
dr over dt.
Good. It's not just radius, right? It's going to be dr dt. We see rate of change. So let's see. What's one way that we can get to dr dt? We could go back to the volume equation and do what?
Find in terms of R.
Yeah, get in terms of r, and r will produce dr dt, which will work. Okay. But we have all this related information. I think we're going to have a shortcut to get to where we need to go without having to start from scratch. And I want to point our attention to this ratio relationship that we've already created. Okay, we have 12r equals 5h. Okay, what if we just go ahead and find the derivative there, right? Because with any equation that's related, we can always find the derivative. So what's 12r's derivative? Remember, time is still involved here. So what's 12r's derivative?
12 dr dh.
12 dr d
T.
t. Okay, good. Yeah, so t is going to always be in your denominator. But good, that's right. R disappears, but we took the derivative for r, so we need that dr dt. Okay, how about the right side? 5h?
5 dh dt.
So this is a lot faster, right? We have dh dt, so we have a clear path to solving for dr dt. So it's nice having this relationship, right? Because if you somehow solve for the wrong variable and you realize at the end, oh wait, the problem is actually for dr dt, you can just quickly get there by plugging into the second equation. So that's what I was saying before, how ideally if you find that you messed up and you solved in terms of r instead of h, you can still get to the correct answer because you have this, you can create a quick derivative equation that can help you connect from one rate to the other. Okay, so let's just finish this problem here. So 12 dr dt. Divide both sides by 12. That's the same thing as multiplying by 1 over 12, right? dr dt, dh dt, these are both one-dimensional units, so still feet per minute. Still negative, right? Height is dropping, radius is decreasing, so the signs make sense. Okay, any questions? Okay, let's turn to the back, and we're just going to finish up with 3 and 4 on the back. 3 is volume surface area equation formula that we did with the balloon that we've seen before. And number 4 is a ladder problem with Pythagorean theorem, and part B with area using product rule. So we're just going to get practice with problems that we already learned how to do. All right, so here's your equation. Go ahead and find your derivative and see how much you can gather using the number 3 that we did yesterday. Right, very similar setup, right? Okay, so spend a couple minutes, see how much you can set up. All right, so I'll make sure we're on the right track here. Helium is being pumped into the balloon at a constant rate of 25 cubic feet per minute. Okay, what is that? What variable is that? Okay, dVdt, positive or negative? Positive, right? Pumped into the balloon, we know the volume is increasing. Positive. At what rate is the surface area increasing? So we're looking for, yeah, ds dt. When the diameter is 16 feet. Now, we don't have diameter, but what's something related that we can use? Yeah, radius is what? Mm-hmm. So we can ignore the 16 now. We have 8 that we can use for our problem. So we're looking for ds dt. We need r. We need dr dt. Looks like we have r already. But we need dr dt, which we don't have. But maybe this dv dt can help us get there. Right? Okay, so see if you can use a couple of steps there to get to your ds dt. Okay, remember to hold on to the pi unless they cancel out.
Wait, Mr. Yang,
Yes.
for dv dt, why are we using the 10 cubic centimeters per second instead of feet cube per minute?
Oh, sorry. Yeah, sorry. That's my mistake. It's cubic feet. Thank you.
So we should use the 25 then, or just use the 10?
Oh,
10.
where did I get that 10? I was looking at the previous
It's from
problem.
the other
Sorry.
problem. Yeah,
Sorry.
you're good.
I was looking at the previous problem. My bad. 25. Sorry. Didn't mean to throw you guys off.
You're fine.
Okay, so okay. Anybody have an answer for number 3?
Say 50.
Okay, 50. You say 50 over 8?
Oh, yeah.
50 over 8.
8 over. Wait, sorry, I confused myself.
That's fine. Take your time. Anybody else have an answer?
ds dt is 6 over 4.
Close. Let's see. Anybody else?
6 and 1/4.
Okay, yeah. 6 and 1/4, 6.25, 25 over 4. Those are all good. What's our unit of measure?
Feet squared per minute.
Yeah. Surface area, right? Focus on that word area, square feet. Time component is minute. Good. So we use the dv dt to help us get to dr dt, and then finally we have dr dt to plug in and solve for ds dt. Either 25 over 4 or 6.25 is fine. Normally I prefer fractions, but if the decimal is exact, then you can do that. If it's a repeating decimal though, then go to your fraction.
Oh.
Small mistake.
I forgot the squared on the.
Oh, right here. Got it.
Yes.
Yeah.
That's the only thing in it.
Got it. Yeah. Yeah, so it's good, you know, with these problems that after you finish the problem that you go back and look at it, or maybe do another problem and then come back to it with fresh eyes and see if you can catch anything you missed. Okay, all right, let's do number 4. Number 4 is similar. It's virtually the same as the ladder problem that we saw before. It's just different numbers. So let's see if we can practice through the steps here. So Pythagorean theorem for A, for B, it's going to be eventual product rule. Let's see if we can finish this problem. Feel free to use the notes that we did from Friday, the first page, and see how much you can fill in. This is the information I gathered from the setup, derivative, and information. See if yours match. I use H here, not consistent. Okay, for A, I got negative 75 over 8 feet per second. That vertical part of my triangle is decreasing, so it makes sense that I'm getting a negative rate. Let's finish off with part B. Area of a triangle, 1/2 base times height. Step through product rule. And then you can fill in the information from part A. Okay, what is our unit of measure going to be at the end for dA dt?
It's gonna be, feet squared per
Yeah.
second.
Good, feet squared per second, okay. All right, check your answer when you're done. So this is going to be the homework for the other classes, but we have a little bit longer period, so we finished the homework, so no homework over the weekend. But Monday, we will do the notes that you printed out for today, and I may add another thing for L'Hopital's rule, so you can check the website Sunday for that additional worksheet I'll put together. But we've pretty much seen all the different types of problem. We have another similar triangle problem to go over, but I think it's easier. It'll feel easier than these cone problems. So we can start review Monday, pretty much after those two additional things we need to do. All right, thanks everyone. Hope you guys have a great weekend.
Thank
See
you,
you
Mr.
guys
Yang.
Monday.
Mr. Yang, have a nice weekend. Bye.
Bye.
Thank you.
Bye, thank you.
Have a good weekend.